Hey guys, we're Team A23, and today we're going to be talking to you about sets, and that includes unions, intersections, generalized unions, and generalized intersections. So, the first thing that we're going to talk about is the union between two sets. So, the union between two sets, let's say A and B, creates a new set that contains the elements that are in set A, set B, or both. This is denoted by writing A or B. It's important to note that elements that are in both sets originally are not duplicated in the union. Rather, only one of the particular numbers in the union. So let's start off with a simple example. Let's say you have the set A, which consists of the elements 1, 2, 3, 4, and 5. Then you have the set B, which consists of 5, 6, 7, 8, and 9. Therefore, the union between A or B is 1, 2, 3, 4, 5, 6, 7, 8, and 9. So it's pretty simple. It's basically just the two sets included. Now let's look at a Venn diagram example of this. Oh, sorry. Jumping back to what we just did, notice that 5 was in both set A and set B. So notice that in the union of A and B, we only listed 5 once, and this is very important because you do not double count the intersection between the two unions, the two sets. So let me clear the board and also describe this using Venn diagrams. So if we were to draw a Venn diagram, and the first circle would represent A, and the second circle would represent B, and then a box to contain both of them. So, now looking at this, you can think for a quick second, what would the union between both of them be? And using the definition we stated earlier, it would obviously be shading in all the area that is encompassed by A and encompassed by B. So this includes the intersection between both. And in a nutshell, that's basically what a union is. So, the next thing that we're going to talk about is the intersection between two sets. So, the definition is simple. Let A and B be sets. The intersection of the sets A and B, denoted by A and B, is the set containing those elements in both A and B. So let's take the sets listed above again. As we said earlier, set A is 1, 2, 3, 4, and 5. And set B is 5, 6, 7, 8, and 9. Using the definition that we just made, the intersection of the two sets, or the elements that appear in both set A and B, are simply 5. That's the only element that is in both A and B. So obviously then you can create the set of the intersection of A and B being just 5. So although this is simple, we can illustrate this once again using a quick Venn diagram. So let me just draw in my my box containing all the elements, and then a circle for A and a circle for B. And now the intersection between A and B is that shaded area right in between them. And so in the case of the sets, 5 would be both part of A and part of B. And in the case of this Venn diagram, the shaded region is again part of A and part of B. So that's basically what it intersects. So going off of the intersection definition, there's also something called disjointed sets. So basically, the definition of this is that two sets are called disjoint if their intersection is the empty set. For example, if set A simply has the element 1, and set B has the elements 2 and 3, using the intersection definition earlier, the set containing the intersection of A and B would be empty, because none of the elements of set A are present within B, and none of the elements in B are present within A. And that's basically what a disjoint set is. Another thing that we can note with two sets is what's called the difference between them. So, to illustrate this, basically, let A and B be sets. The difference of A and B, denoted A minus B, is the set containing those elements that are in A but not in B. So we can use a quick example to illustrate this. Let A be the set containing 0, 1, and 2, and let B be the set containing 1 and 2. Therefore, the set A minus B is simply 0, because that is the only element that was in A and did not get it subtracted away from B. So once again, this is pretty simple, but that's basically the difference in sets. Going off of this definition of the difference of sets, we can also start to formulate a picture for what the complement of a set is. So let U be the universal set containing all elements. The complement of the set A, which is denoted A prime, is the complement of A with respect to U. Therefore, the complement of the set A is U minus A. So a way to visualize this is if you have the set A and you take U minus A, you can therefore get the complement of A. So, now that we have a better idea for what unions and intersections are, there are many applications that you can do with these. And, we can't get through all of these in this video, but one example is the distributive property. And the distributive property is pretty simple, and it's as follows. Let's say you have the expression A and then the union of B or C. That is equivalent to saying A and B or A and C. So that's an example of a simple property that can be derived, and one way you can derive this is using a truth table. Another application of these is called the De Morgan's laws. And basically, this kind of takes advantage of the negation operator that we used last time. And it's pretty simple. It states that if you have the expression not A or B, that is equivalent to saying not A and not B. Similarly, if you have the expression not A and B, that is equivalent to saying not A or not B. And those are De Morgan's laws. It's once again, you can derive this using a truth table, but once you know these laws, it really helps you simplify much bigger and larger expressions. Finally, the last topic we have to discuss are generalized unions and intersections. So, basically what these are ways to write out much longer unions and intersection sets of different sets in simple notation. So, basically the notation for a generalized union is as follows. The union of set 1 and set 2 and set 3 all the way to set n is simply denoted as the union from I equals 1 to n of set I. So it's pretty simple in practice. Let's say set 1 simply has the element 1. And set 2 has the element 2. Set 3 has the element 3. And, this pattern continues all the way until set n, which just has the element n. Therefore, the union of all of these sets, or if I were to write it like this, I equals 1 s of I, is simply equal to the set containing 1, 2, 3, all the way up to n. So pretty simple. So now let's adjust this example a little bit so that we can talk about intersections. So let me just write up here. This next part is for generalized intersections. And now it's the same idea as before. It's to discuss the set, if you have set 1, set 2, all the way up to set n, you can denote this simply as the intersection from I equals 1 to n of the set I. So now, the only thing different from unions is that the practice is actually a little bit different. Rather than taking the union of all the sets, we would take the intersection. So let's say set 1, as before, has the element 1. However, and set 2, this time we're going to change it. We're going to say set 2 has the elements 1 and 2. Set 3 has the elements 1, 2, and 3. And this pattern continues until set n, which has the elements 1, 2, 3, all the way up to n. So it has n elements. The intersection, the generalized intersection of this, is therefore just 1. And the reason being for this is because 1 is in all of the sets. And therefore it is the intersection of all of them. And that's basically a comprehensive overview of both generalized unions and generalized. So we hope you enjoyed our presentation. We have presented a conclusion slide here, kind of recapping everything we talked about. As you can see, set A contains the elements 0, 1, 2, and 3, while set B contains the elements 2, 3, 4, and 5. The union of B would consist all of the elements, so 0, 1, 2, 3, 4, and 5, whereas the intersection would only contain the elements that are found in both, therefore being just 2 and 3. So, from these definitions of unions and intersections, we can kind of go a little bit into different properties. I've just put the distributive property here that we talked about, and that is if you have the intersection of set A and the set containing the union of B and C, that's equivalent to the union between the set containing the intersection of A and C and the set containing the intersection of A and B. And then at the bottom we have the notation for generalized intersections and unions. And basically what this describes is a set of n different sets that can be encompassed by either one intersection between all of them or one union between all of them. So anyways, that's all the information that we have. I hope you enjoyed it, and feel free to contact Group A23 if you have any questions about unions, intersections, or other properties.